Hello everyone and welcome. This is Sivaganesh from UpID. Today we are diving into essential principles of relational database design. In this presentation, we'll explore a structural methodology for creating efficient and accurate databases based on the extended entity relationship model. We will be discussing how to efficiently model data requirements, transform those models into relations, and ensure data integrity through normalization. Whether you're a student, a developer, or simply interested in how data is organized, this overview will provide with you valuable insights. So let's get started. We are presenting a logical database design methodology for relational databases. This methodology developed by Toby Theory, Zhongying Yang, and James Fry provides a structured approach to designing efficient and accurate relational databases, addressing the complexities of large scale database design. So coming to the introduction, traditionally relational database design used a bottom-up approach, synthesizing data elements into normalized relations. However, this became very complex in large databases, often overwhelming designers with the sheer number of data elements and their independence. A top-down approach based on the universal relations assumption, where all attributes are initially considered within a single relation, has been explored theoretically. While elegant, it's not always practical. So, in practice, a combined approach is most common. This paper uses a entity relationship model, which is effective for communication between designers and end users due to its intuitive graphical representation. So, coming to the ER model, the ER model represents a database in terms of entities, attributes, and relationships. Entities are the fundamental objects about which data is collected, for example, customers, products, and so on. Uh, Attributes describes these entities. Identifiers are attributes that uniquely identify an entity instance. For example, customer ID we can choose for this time. So while descriptors provide non-unique information, for example, customer name. So entities can be strong, having their own unique identifier, or weak, depending on another entity for their identification. Relationships define how entities are associated. Their semantics include connectivity and participation constraints, indicating whether entity participation is mandatory or optional. So coming to the extended ER model, so while effective for basic database representation, the original ER model has limitations in capturing more complex real-world scenarios. Uh, it lacks abstraction concepts needed for view integration, which combines different user perspectives of the data. So it is also doesn't fully address how to handle data integrity issues, particularly concerning null attribute values in relationships, and it can be awkward to represent relationships involving more than two entities. The extended ER model was developed to address these limitations, providing more expressive power while retaining the simplicity and clarity of the original ER model. So coming to the subset and generalization hierarchies, the extended ER model introduced subset and generalization hierarchies to model complex data relationships. A subset hierarchy defines potentially overlapping subsets of an entity. For example, an employee entity might have subsets like employees attending college or employees who was shareholders, for example. A generalization hierarchy, on the other hand, partitions an entity into strictly non-overlapping subsets. For example, this employee might be generalized into engineer, secretary, and technician as example. So both hierarchies enhance modeling capabilities but differ in how instances are classified and updated. So coming to EER construct. So extended entity relationship constructs provide more precision in defining relationships. The degree of a relationship indicate the number of participating in entities, which is unary, binary, and ternary relationships involve one, two, and three entities respectively. So connectivity specifies how entity occurrence relate to each other, which is either one-on-one, one-to-one, one-to-many, or many-to-many. Cardinality provides further details specifying the exact number of allowed instances. For relationships with a degree greater than 2, we use n-sided polygons to represent the connectivity of each participating entity, clarifying indicating whether it is one or many. Coming to extended entity relationship constructs, another important extended entity relationship construct is membership class, which specifies whether an entity participation in a relationship is mandatory or optional. For example, if every officer must be occupied by an employee, then the employee's membership in the occupies relationships is mandatory. The basic object in entity extended entity relationship models are n array relationships and their associated entities. So abstraction introduces generalization and subset hierarchies. Generalization implies disjoint subsets, while subset hierarchies allows overlapping subsets, offering different ways to model real-world scenarios with varying constraints. So extended entity relationship modeling of requirements. So the first step in the methodology is a through requirements analysis. This involves understanding the data requirements of the enterprise, which includes describing the objects, which is entities, and their association, which is relationships. So it also involves determining the types of transactions to be executed on the database. Um, Processing requirements are captured using natural language expressions along with their frequency of occurrence to understand how the database will be used. Uh, Finally, logical views from different user groups or departments are integrated into common global view, providing a unified representation of the data requirements for the entire database. So coming to the transformation of the extended entity relationship model to relations, the second step in the methodology transforms the extended entity relationship model into a set of candidate relations, which are essentially tables into the relational database. So this transformation process involves categorizing the various extended ER constructs, applying a defined set of mapping rules to convert these constructs into relational schema, generating the initial set of relations, and then eliminating any redundant relations that may have resulted from the transformation. This step is crucial for bridging the gap between the conceptual entity relationship model and the logical relation model, preparing the design for the normalization process. Normalization of a relation. The third and final step is normalization. Here we analyze the candidate relations generalized in the previous step to ensure they meet the described level of normalization. This involves deriving functional dependencies from the extended entity relation diagram and the requirements, representing how attributes are related to each other. Multivariate dependencies are also considered, which arise in certain complex relationships. Candidate relations are then decomposed and modified to achieve the highest desired degree of normalization. Uh, any remaining redundancies are analyzed and eliminated, ensuring that data integrity is maintained and the database is structured efficiently to prevent update and anomalies. So, coming to the results and conclusion. In conclusion, this methodology offers several key advantages. It enables the creation of database design that accurately affect real-world requirements and are flexible enough to adapt to future processing needs. By using the extended entity relationship model, it integrated through the normalization process, resulting in a database that is both reliable and simple software tools, making it practical for a range of applications and development environments. So, coming for the ideas for future research, The paper also identifies several promising areas for future research. These include automating the methodology to streamline the design process and reduce manual effort, extending the model to incorporate additional semantic constraints for even greater accuracy and expressiveness, focusing on performance evaluation and optimization for the resulting database design to ensure efficiency and integrating the methodology with other existing database design tools and techniques to create a more comprehensive and unified database design environment. So these future directions aim to enhance the methodology's applicability, efficiency, and overall effectiveness in the real world database development. So this is our presentation on relational database design. We have explored a methodology that emphasizes accuracy, flexibility, and data integrity. Hopefully, you found this informative. So good. Thank you.